guys, Tan Chen Hao here, and today I'll be talking about relativistic electromagnetism and the interesting effects that arise from considering relativity in electromagnetism. So first of all, I just want to credit this book for providing a very valuable explanations for this topic. So this is the overview of what we're going to do. We're going to first talk about electrostatics, then what happens when you have electrostatics that are moving. This gives rise to a Lorentz transformation of electric fields. Then we're going to talk about what happens when the source and the test charge is moving relative to each other, and that will give rise to another effect called the magnetic field. Then we'll talk about magnetic induction, which is the creation of a non-conservative electric field by a time-varying magnetic field. Then we'll talk about Maxwell equations, then four vectors in the context of relativistic invariance, and then as a fun side note, we'll talk about gauge invariance and a bit of QED. Of course, I'm not an expert on QED, but I would like to just briefly mention it. So first of all, okay, so this is the overview of all the equations that we're going to eventually cover. We're going to go through a bunch of thought experiments as well as real experiments, and we're going to show how the apparent paradoxes are resolved using the Lorentz transforms of the electromagnetic fields. Of course, this is not conclusive evidence for the Lorentz transformations. It's merely suggesting that we need the experiments merely suggest that we need some sort of transformation that makes the experiment make sense. So after all, the Maxwell's equations are a set of postulates which have been verified by experiment, and it is a model of how we believe it works. We can't be absolutely certain that it is a complete description. So anyway, getting on to the electrostatics. The idea is that charges produce fields. With a charge density rho, it creates an electric field, and that gives us our first Maxwell equation. Then how do we know charges creates fields, but how do charges respond to fields? Well, there is the force, the electrostatic force, and additionally, the electrostatic fields created by charges or charge distributions, they are conservative. This can be verified because we know the form of the electrostatic fields, and then we take the curl, we realize it's zero, so that implies that the electric field can be written as the gradient of some scalar function, and this is known as the potential. We'll see later that this curl of E0 breaks down in the context of time-varying magnetic fields. So let's move on to moving charges. Electrostatics plus relativity gives you electromagnetism. So first, let's consider a parallel plate system. Okay, then we have two observers. One is the lab frame and one is a moving frame. We know that in the moving frame, the lengths contract, but because of something known as charge invariance, which is an experimental fact, because of charge invariance, that will imply that the lengths contract, and hence the charge densities have increased. And since the charge densities increase, the electric fields created by these two plates would have increased in the moving observer frame. So how do you do that? You do the following procedure. The key to take note is that the invariance of charge here is an experimental fact, right? And this would suggest that in order to let the theory be self-consistent, we need to resolve it by allowing the electric fields to Lorentz transform in the following manner. Later you'll see that there's additional V cross B term, but for now this is how it transforms. Okay, now for magnetic fields, imagine you have a moving charge and a moving source. Previously we only had a moving source. Now we have a moving charge, and how does it respond to a moving source? We consider a current carrying wire. Let the current carrying wire be neutral in the lab frame. So what this means is that the bunch of positive ions and a bunch of moving electrons. Now these moving electrons have have the same charge density as the ions. However, do note that the electrons are moving with velocity v naught, so it is length contracted. So in the electrons frame, the charge density would be lower than the ionic charge density. So then we consider two observers again. Okay, so we say that there's going to be a force that acts on the charge. And how do we know this force? How do we know what's the force acting on the charge that's moving with velocity v? We Lorentz transform it into the frame moving at velocity v. So when you Lorentz transform into the moving S prime frame moving at velocity v, you get a transformed ionic charge density as well as a transformed electronic charge density in the following manner. The new charge densities will give rise to an electric field, and this electric field would result in a force observed in the moving frame given by this line over here. Then of course, if we want to measure the force in the stationary lab frame, then we need to Lorentz transform the force again back into the lab frame, and we obtain this expression. We realize that this looks very similar to the magnetic field, and in fact we define it as a magnetic field. So if we redefine, so this force does not arise out of electrostatic origins, right? Because from the lab frame, the charge of the wire is neutral, so there's no electrostatic force. However, we still observe such a force due to the requirement of Lorentz invariance. So we have to redefine our notion of a force on a particle, and we redefine it as the electrostatic force QE plus the Lorentz magnetic force, which is V cross B. The whole thing here is called the Lorentz force. So you can see that, so what is this B field over here? Is defined as this for a straight wire. Now, using this expression, we can do a line integral around the wire. Do a line integral, and we realize that it is equivalent, the integral of B dot ds around the wire is equals to the current. Now we postulate, remember that this is a postulate, and after all the Maxwell's equations are postulates. We postulate that this holds for a wire that is not completely straight as well. And if we apply Stokes' theorem, we get the Amperes Law, and it's going to be one of Maxwell's equations. However, it's still missing a term over here, which we will add later. Now, so if we have the curl of a magnetic field, and in order to solve for the magnetic field, the vector field, we need to know the divergence as well. So since there's no experimental evidence for magnetic monopoles, we postulate that divergence B is 0. This allows us to write the magnetic field as a curl of some other vector field called the vector potential, and we'll see later this has interesting properties, namely gauge invariance. Okay, so then how does the magnetic field transform under Lorentz transformations? So we consider two charged plates with charge density sigma, and they are moving, and the charge plates are moving. Two infinite charge plates are moving. Then we Lorentz boost into a moving frame. So initially, the magnetic field is given by this, and the electric field is given by this. However, in the new moving frame S prime, the charge densities would Lorentz transform because the lengths contract, so the charge densities would increase. The charge densities would decrease, I believe. Then as a result, the new magnetic field is now given by this expression, which can conveniently be expressed as the old magnetic field and the old electric field. And the new electric field, due to the new charge density is also expressed as such. Now we can generalize this to the following expressions for the perpendicular electric fields and the perpendicular magnetic fields. Perpendicular in this case refers to the direction of the magnetic field relative to the Lorentz boost. So in this case, you see the B pointing up, that would be perpendicular to your direction of the Lorentz boost V. Additionally, the magnetic field in the parallel direction of the velocity of the Lorentz boost, it remains unchanged. So now we have covered how the electric fields and magnetic fields Lorentz transform under a Lorentz boost. Let's talk about magnetic induction. So once again, we bring out Lorentz invariance. So let's say we consider the scenario of a charged rod moving in a magnetic field. The charged rod has mobile charges, namely electrons, and when the charged rod moves in a magnetic field, according to our Lorentz force law, the charges would experience a force. This would cause a redistribution of charges, and we consider it in the two frames. First is the stationary lap frame. So in the stationary lap frame, the rod is moving through a magnetic field, and that causes a Lorentz force to be experienced by the charges, which causes a redistribution of charges. You can see positive on this end, negative on this end, until and this redistribution of charges will cause an electric field to build up within the rod itself, because electric fields come from the electrostatic fields come from charge distributions. This would occur until it reaches an equilibrium where the forces balance out, the electrostatic forces and the Lorentz force balance out, and as a result, an electric field will be developed in the rod. Now what happens when we Lorentz boost to a frame moving with the rod? In that case, the velocity of the rod is 0. So it seems like since the rod is not moving in a magnetic field, there's no Lorentz magnetic force, right? Indeed, that is the case. However, accounting for the fact that once you Lorentz boost into a new frame, the electric fields Lorentz transform as well, and you see that the perpendicular electric fields it becomes V cross B. So in a sense, now the charges would also redistribute, but the charges redistribute due to the new electric fields that come from the Lorentz transformation instead of the Lorentz force. So once again, I repeat, in the original case, in the first scenario, in the stationary lap frame, the forces acting on the charges that causes the redistribution of charges is the Lorentz force, because the charges are moving in a magnetic field. However, in the rod frame, there's no Lorentz magnetic force because the charges are not moving in a magnetic field. However, the charges will still redistribute due to the presence of an electric field now that we are in a new frame of reference. So that is how you resolve the apparent paradox. Yeah, if you do not consider the new electric field, you will get a paradox, because in one frame you see an asymmetric charge distribution, and in the other frame you will not see a charge distribution. So once again, we see that Lorentz transformations resolve the apparent paradoxes that come from such scenarios. Okay, now let's consider what happens when you have, we know that, let's consider what happens when you have a loop of wire that's moving through a non-uniform magnetic field. So what happens is that one length of the wire, let's say we have this rectangular loop moving through magnetic fields. On one side is B1, on the other side is B2. One side is different from the other, perhaps one side is stronger. So if we consider the Lorentz force on the charges along the loop, and we do the integral along the loop, we actually get that the line integral along the loop is non-zero. So the EMF is the force per unit charge that the Lorentz force acts on the charges in the wire. So in other words, you see that the Lorentz force causes charges to move in the loop, because the Lorentz force is in a sense different on one side relative to the other, because one side's magnetic field is stronger. So if you do EMF, you realize that the reason the charges are moving in a loop is because the Lorentz force on one side is stronger than the other. However, what becomes interesting is when we Lorentz boost to a frame where the conducting loop is now stationary. So in this case, there is no Lorentz force. However, physics must still be the same and the charges must still move in a loop. Now, how would that be so? That would arise because the electric fields, the Lorentz transformed electric fields, are now different on each side. And more interestingly, if we take the integral of E dot dl, we get a non-zero value. And we realize that in the previous scenario, we said that the curl of E is 0. In this case, it's clearly violated. And this electric field, this non-conservative electric field, now causes charges to move in the loop. Now how can that be? I mean, we've violated this. And indeed, we need to amend the curl of E equals to 0. We need to amend that law because it's now a non-conservative electric field. So, to reiterate, the electrostatic charge distributions will give rise to conservative electric fields. However, when you have a magnetic field that is changing in time, or a magnetic field that is stronger on one side relative to the other, it can indeed give rise to non-conservative electric fields. So and then we consider one more scenario before we amend the law, which is what happens if our loop is not moving at all, but instead our magnetic field is changing. Now, experimentally, it has been found out that there is no experimental difference between a moving magnetic field and a changing magnetic field. In other words, the loop is blind to the source of the magnetic field. The loop will only feel the magnetic flux going through it. So this allows us to define the universal law of induction, which is basically the EMF is equals to change in magnetic flux. So with that, we can use Stokes' theorem to rewrite it as curl of E equals to minus B over dt. So this is now the non-conservative electric field when there is a changing magnetic field. So this is very unintuitive, and yeah. So now we have completed all four Maxwell's equations. Oh wait, we have not completed it yet. We are nearly there. The last amendment that needs to be done is the Amperes Law. So we consider a scenario where we have a capacitor that is charging up. So we realize that since there's current flowing in the wire, there is a magnetic field generated along the loop C. However, if we think of it as the current density J, the current density that is passing through the surface S is currently 0. So clearly it's a violation because the current density passing through the surface S is 0, yet there is a magnetic field. So how can we resolve this? Well, we resolve this by noticing that when the charges flow into this parallel plate capacitor, then the electric field would increase. So we postulate the addition of this delta E over delta T term, and we include these constants to make sure it's dimensionally consistent. So now this new term E dot dA, realize that there should be a time derivative here, I'm sorry. We realize that this new term, it now accounts for the magnetic field along loop C. So the new Amperes law after Stokes' theorem is now curl of B equals to current density plus the change in electric field with respect to time. And with these four, we are complete. The Maxwell's equations are complete. So these four equations are the postulates for the dynamics of the electric and magnetic field. And we have also previously seen that through a bunch of thought experiments as well as real experiments, that the electric and magnetic fields Lorentz transform in such a way to ensure that the forces make sense in all reference frames. So now let's talk about four vectors. We can express the electric and magnetic fields in four vector notation to see the relativity more clearly. So let me just go back to the Lorentz transformations here. It turns out that these four Maxwell's equations, they are invariant under Lorentz transformations, meaning that if we work in one frame, we set up the Maxwell's equations, we set up the Maxwell's equations in one frame, and then we Lorentz boost to a new frame, the new electric and magnetic fields in the new frame would also obey the same Maxwell's equations. This is also called Lorentz covariance of the theory. So how clearly the link between these two is not very obvious right now, like it's not clear. So let's go to four vector notation to see how we can make the Lorentz invariance more manifest itself more clearly. So we define a vector potential to be the scalar so we define a bunch of four vectors first. First thing is the potential, the four potential, which is the scalar potential and the magnetic potential, which we previously introduced. Remember that then the electric and magnetic fields can be defined as the following way. And then we can introduce this thing called the Faraday tensor or electromagnetic tensor as the derivatives of these four potential. We also introduce charges, and the time derivatives is just, So from this expression, we can observe that the electric and magnetic fields can be written as in the following manner in terms of the Faraday tensor, the electromagnetic tensor. And if we invert the relations, we solve for F, then we obtain the following electromagnetic tensor. Do note that here I'm setting C equals to 1 to make the equations neater, and in the end, if we want to get experimental results, we can just put back the factors of C with dimensional analysis. So this is the electromagnetic tensor. So why is that useful? It's useful because the Maxwell's equations, two of the Maxwell's equations can be written very compactly as such, and this also gives rise to charge conservation because F is antisymmetric. And the other two Maxwell's equations actually come from the definition of F, and this is known as the Bianchi identity or Bianchi identity. Now, for the Lorentz invariance of the electric and magnetic fields, it is manifested in the way the vector potential, the four potential, Lorentz transforms, and the corresponding transformation of the electromagnetic tensor. Now the charges also Lorentz transform, and with this new notation, because we are using four vector notation, the equation here, the non-homogeneous Maxwell's equation, is manifestly Lorentz covariant because of the following Lorentz transforms. So if you plug these in to here, you realize that both sides cancel, and the equations describing the dynamics of the electric and magnetic fields are invariant under Lorentz transformations. So you can see that through four vector notation, we've actually simplified the equations down greatly and made it very clear that the equations are Lorentz invariant. Now there's an interesting property of the vector potential, and it is called the gauge invariance. So if this is a vector potential, we realize that if we do a following transformations on the scalar potential as well as the vector potential, so we add a factor chi over here. There's a function chi over here. Chi is a function of space and time. So if we modify the four potential in the following manners, then we realize that the magnetic field actually does not change, because the curl of a gradient of a scalar function is 0, and likewise the electric field does not change as well, because the new term over here, the chi term, will cancel out with the transformation of A. Or if we want to write it, so we realize that if we can add an additional factor, we can add additional function, it's called a gauge field. We can add this gauge field chi to the potentials without changing the magnetic and electric fields, and that will mean that the Maxwell's equations have a degree of redundancy. More clearly, in relativistic notation, the four potential transforms in the following manner, and the Faraday tensor would be unchanged, and that makes sense because the Faraday tensor has electric and magnetic field as its components, so of course it must not change. Now, why is this useful? Because it's useful because with the vector potential, we can solve Maxwell's equations. It can help us in solving Maxwell's equations. So for example, we want to find the magnetic field of a current carrying wire. How do we do so? We know this is the Amperes law, but solving this is difficult, so we write it in terms of the vector potential using the curl of a curl formula. And because we can add any gauge field, we can gauge transform A in any way we want. We can use this additional degree of freedom to set the divergence of the vector potential to be equal to 0. So let me reiterate. In this case, we saw that there's a degree of redundancy for the vector potential. We can add the gradient of any scalar function, and the magnetic and electric fields will not change. So in other words, we can use this as a tool, a useful mathematical tool, because in certain gauges the equations become simpler. So in this case, we set the divergence of the vector potential to be equal to 0 because it will simplify equations, and this is just Laplace equations. Then Laplace equations has the following solutions, and hence if we want to, and hence this is the solution. So we want to find the vector potential of a current carrying wire. We just replace J dV with I dl, where I is a constant, so you pull it out. So you integrate across dl over r, where r is the distance from this differential line element to the area of interest, to the coordinate of interest. So for a small length of wire, the magnetic field contribution is given by curl of dA, which is basically the constants times dl over r. So what is the curl of this thing? We can apply the product rule and notice that dl is constant, so we just need to care about the gradient of 1 over r. The gradient of 1 over r is this, and multiply out, we get dB equals to this constants over here times dl cross r hat over r square, and this you might recognize as the Biot-Savart law, So you can see that by working in the vector potential, we have solved Amperes law to obtain the magnetic field of a differential length of wire. So you can see that there are more in more advanced electromagnetism, the vector potential is a very, very useful tool. And yeah, when you want to solve systems where the charges are, and Biot-Savart law does not apply in all cases. There's when the charge distribution, when the charge density, no, when the current density is a function of time, you need to do something called that you need to account something called retarded time, but that is for the scope of another video. So lastly, we have seen that there's gauge degree of freedom in electromagnetism, and how does that tie in with quantum electrodynamics? which is basically the theory of fermions. So first of all, before going on to fermions, let's talk about the Lagrangian for electromagnetism. It turns out we write the Lagrangian as the following manner, with the coupling term of the vector potential to the charges, the sources. Then by applying Euler-Lagrange equations, we can obtain the following, which is basically the non-homogeneous Maxwell's equations. The other two Maxwell's equations comes from the definition of F itself, using the Bianchi identity. Now there's this awesome video by Dietrich Lab that covers this process very clearly, but just note that this is the Maxwell Lagrangian. So this is the Lagrangian in Lagrangian mechanics describing the dynamics of the electric and magnetic fields. So how do we go on to couple electromagnetism to spinors, to fermions? We do a simplified model first to illustrate the idea. If we have a complex scalar field theory, and this complex scalar field theory possesses U1 global gauge invariance. This is basically a phase. It's a unit complex number, which is why it's U1. And so it possesses this global gauge invariance. We do this process called minimal coupling, and we basically upgrade the global gauge invariance, this phase factor, we upgrade it to be a function of space-time. So if it's now a function of space-time, clearly these derivatives would not like it. These derivatives would pull out this dependence on space-time, and in order to fix that, we need to introduce covariant derivatives. These covariant derivatives are defined as such with the gauge field here, and with this new definition of the derivative, the covariant derivative, we can check that if we can check that it obeys local symmetry, provided we transform the gauge fields in a certain manner as well. And transforming the gauge fields is completely legal because we previously showed that there is a gauge degree of freedom. So if we add, so after this is the complex scalar terms. Then we add on the gauge field dynamics so that the gauge fields can have a life of its own, and we obtain the coupling. So we obtain the scalar fields, we obtain the gauge fields, which is electromagnetism, you see here, and then we obtain the coupling between them. And this is our complex scalar field theory with local U1 gauge invariance. Now, to upgrade it to quantum electrodynamics, it becomes a bit more complicated because the complex scalar fields now become spinors. These are 4-component spinors. They're called Dirac spinors, and the equation of motion via the Euler-Lagrange equation would give us the Dirac equation, which describes Dirac spinors. So, but the procedure for adding gauge invariance is still the same, because if we want to allow for local U1 gauge invariance, we use covariant derivatives to ensure that the theory is locally invariant under gauge transformations. Locally invariant under U1 gauge transformations, provided once again that the gauge fields transform by themselves. So we add the additional gauge field dynamics, and now we have a QED Lagrangian which describes Dirac fermions, which is this term over here, U1 gauge bosons, which is electromagnetism over here, as well as interactions between the fermionic fields as well as the gauge boson fields, which is this last term over here. So that is an overview of what QED is. Of course, there's a lot more to it. After you get a theory, you still need to do a lot of procedures. You need to calculate propagators and perturbative expansions, which will give rise to your Feynman diagrams. But that is definitely out of the scope of my knowledge. So that is all I have for today. Thank you very much.